a conjugate of a complex number. So if we have the complex number z, which is a plus j times b, then the conjugate of this complex number, or the complex conjugate of this complex number, is given by the complex number that you get by keeping the real part as it is and negating the imaginary part. Or so you get the complex number a minus j times b, and this is called as the complex conjugate of z. It's usually written with a z star, or sometimes it's even written with a z bar. In this course, we are pretty much going to use a z star to represent the complex conjugate. If z is represented in polar form, so if z is written as r times e to the j theta, then z conjugate is given by r times e to the negative j theta. And you can see that this is true because if we write z as r times cosine theta plus j times r times sine theta, and z conjugate then would be given by r times cosine of negative theta, but cosine of negative theta is the same as cosine theta, whereas the imaginary part will be given by r times sine of negative theta. And we know that sine of negative theta is the same as negative sine theta, so we get negative j times r times sine theta, and you can see that these two complex numbers are conjugates of each other. Okay, so pictorially, a complex conjugate is something you get by simply flipping the complex number about the x-axis. Now, in these kinds of examples, it's pretty easy to see what a complex conjugate is, but sometimes you may have to take the complex conjugate of expressions which look a little bit messier. In which case, the easy way to try to compute the complex conjugate is to replace j by negative j in these expressions. Okay. Now we'll quickly go through a few properties of what happens when you add a number and its complex conjugate, so on and so forth. So let's think about what happens to when we add z and z conjugate. And you can see that z is a plus j times b, and z conjugate is a minus j times b. So when I add z and z conjugate, what we get is simply 2 times a, or this is 2 times the real part of z. Right? In the same way, if we subtract z conjugate from z, we're going to get 2 times j times b, or equivalently 2 times j times the imaginary part of z. Or equivalently, we can say that the real part of z is given by 1/2 of z plus z conjugate, and the imaginary part of z is given by 1/2, 1/2j times z minus g conjugate. And in fact, this is important. I've seen a lot of people make mistakes by not putting the j in the denominator. So it's 1/2j times z minus z conjugate. What about z times z conjugate? I'll give you a minute to think about that. If you want to pause the video and think about that. So z times z conjugate, it's easier to understand if you think about the polar representation of z and z conjugate. So when we multiplied z and z conjugate, we're going to get r squared, and e to the j theta and e to the negative j theta are going to cancel each other out, and indeed we are simply going to get r squared, but r is nothing but the magnitude of the complex vector, so z times z conjugate is the square of the magnitude of the complex number. Now, I'm pointing these things out because when you do expressions, sometimes you will end up with several terms in an expression, and some of these terms may be complex conjugates of each other, or maybe product of z and z transpose, and realizing these things will help you simplify the expressions. Often, these expressions in the end may be simple if you know how to use these properties to simplify them. Okay, there are a few other properties of complex conjugates that we can quickly go through. So if we have Z1 plus Z2 and we take the complex conjugate of Z1 plus Z2, we can see that this is the complex conjugate of Z1 plus the complex conjugate of Z2. I'm not going to prove this here. You can just write out the Z1 and Z2 in terms of, maybe we say that Z1 is A1 plus J times B1, which is R1 times e to the j theta 1, and let's say Z2 is A2 plus J times B2, which in polar form is written as R2 times e to the j theta 2, and you can simply verify these expressions. And this is true if you subtract Z1 from Z2 as well. Similarly, Z1 times Z, the conjugate of Z1 times Z2 is the conjugate of Z1 times the conjugate of Z2. To see this, you can look at the polar representation for Z1 and Z2. So the conjugate of Z1 times Z2, you can see here, is R1 times R2 times e to the negative j theta 1 plus theta 2, which is indeed the product of e to the R1 times e to the j theta 1 times R2 times e to the negative j theta 2, which is, so this is Z1 conjugate and this is Z2 conjugate. Okay. And if you keep these in mind, it will make arithmetic simpler. So how about Z1 over Z2 conjugate? Well, you can see Z1 over Z2 conjugate is R1 over R2 times e to the negative j theta 1 minus theta 2. Right? Now, indeed, this is equal to R1 times e to the negative j theta 1 divided by R2 times e to the negative j theta 2, which tells you this is indeed Z1 conjugate divided by Z2 conjugate.